Hi and welcome to the Intelligent Auto channel. Today we have this 2015 Ford Transit Connect. It's the 1550 diesel and the customer complaint is it's very difficult to start. Now this van has come to me from another garage. It's actually a garage in North Yorkshire, so it's travelled about 70 miles to get to me. The garage that sent it here have spent quite a bit of time and quite a bit of money on this van trying to get to the bottom of the problem. I'll just read from the job sheet what they've replaced. So far they've replaced the injectors, the high pressure fuel pump, the fuel filter and fuel filter housing, all of the plastic fuel lines, the engine coolant temperature sensor, the mass airflow sensor and also the glow plugs. And I've been told that none of these parts have actually made a difference to the way this van starts. The van was brought to them by their customer with the complaint of it won't start. Now what the customer did say was he seems to think it starts okay if the ambient temperature displayed on the dashboard is lower than 9 degrees. What I've experienced so far is it doesn't. I've had the vehicle parked outside and the ambient temperature has been 6 degrees and it still won't start, or it still struggles to start. What he said is, once the engine's warm, if you switch it off, leave it for an hour, again it becomes difficult to start. If you switch it off and immediately go to start it again, it will restart immediately. Once it's running, apparently it runs fine without any issues and you can drive the vehicle all day. I've already had a look at this vehicle and I believe I've found the cause of the problem. And guys, you're in for a treat today because we've got the big guns out. Today we're going to be using the ThinkCar Max as a diagnostic platform. We're also going to be using the Picoscope along with the low amps clamp, the high amps clamp, and also the WPS 500 pressure transducer. We'll also be doing some bypass testing, and for that we're going to be using a decade box. So like I said, you're in for a treat today. So first of all, let's confirm the customer complaint. So we've got the diagnostic tool hooked up. We'll turn the ignition on and we'll scan the car. It'll auto ID this van by VIN number. There we go. And there we have the topology of the car. So we do a smart scan. Got a medium speed network and a high speed network on this vehicle. The ABS and the body control and the powertrain control module are all on the high speed can. On the medium speed will be infotainment, etc. Aircon. Once again, if it shows in green, it's normal. If it shows in red, it's abnormal. If it shows in grey, that module is not fitted. So no faults anywhere in the vehicle. We're going to go straight to the PCM. See, we've already seen there was no faults in it. I'll just prove to you. No DDCs. We'll go for data. Now with any poor starting vehicle, the first thing I would look at is, does it have fuel pressure? So fuel rail pressure, kPa. Also we'll look for temperatures. So we want the ambient air temperature. We want the air charge temperature. Don't need the catalyst temperature. External temperature. Intake air temp 2. Intake air temp 1. And we're looking for coolant temp as well. So the air charge temperature is 13 degrees, the ambient air temperature is 12 degrees, the engine coolant temperature is 12 degrees, the external temperature is 12 degrees, which is the same as the ambient. Intake air temperature 2, which is part of the boost pressure sensor, is 13-14 degrees, and the intake air temperature 1, which is part of the mass airflow sensor, is 19 degrees. So could that be where our fault lies? I'm now going to also put on the glow plugs. So glow plug, all the glow plug data. At the minute the glow plugs are off, cycle ignition, they stay off. When we crank it, do they stay on? And at this point here, we're going to prove the customer complaint. Glow plugs are coming on, vehicle's still not starting. Try to start there. As you can see, an extended crank time. Glow plugs were on, but what did we find before was this intake air temperature is sitting higher, considerably higher than the rest of the temps. It's quite cold in here today, so the ambient air temperature 12 degrees, which is probably about right, so we'll use that as a datum. And then every other temperature, the coolant, the air charge temperature, all there or thereabouts. But the intake air temperature in the airflow meter is sitting at 19 degrees. So straight away, we can see there's a possible anomaly there. Now this vehicle, I'm being told, has had a mass airflow sensor fitted, and the temp sensor is part of the mass airflow sensor. So let's go to the airflow meter, let's take a look at the temp sensor and see if we can bypass that and bring that down to a temperature which comes in line with the ambient air temperature in the workshop today. So we're in under the bonnet. As you can see, the intake air temperature is sitting at 20 degrees there now. So I'm just going to unplug the airflow meter. And what I'm going to do is, I want the airflow meter to still register airflow, but what I want to do is take the intake air temperature sensor out of the circuit. So to do that, I'm going to use these things, breakout leads. One by one, we're going to break into the circuit. So that pin there goes to that pin there. The next one, pin 2, goes to pin 2 on the plug. I've already checked the wiring diagram for this, and I know that it's the pin to the far right, which is the temperature sensor circuit. So what I'm doing here is I'm keeping the airflow meter in circuit. I'm going to take the temp sensor out of circuit, and I'm going to replace that with a decade box. Got the decade box here. Basically what a decade box is, box full of resistance. So we use this because a temp sensor circuit is just a resistor which is variable depending on temperature. We replace the temp sensor with the decade box, and then we can control the temperature that the ECU sees. So I'm now going to turn the ignition back on, and we'll see on screen as I start changing resistance in the circuit, the temperature on the intake air temperature sensor circuit will start to change. So I'm going to zoom you in on the temperature. Now, as you can see there, it's now sitting at 143 degrees because I've got it out of the circuit. But as I start flicking switches, you'll see that's starting to change. So they're 81 degrees. So that's with 300 ohms of resistance in the circuit. 3 kilo ohms gives me 14 degrees. We're getting somewhere close. We'll start adding a bit more resistance. That's 3,200 kilo ohms. Not quite enough yet. There we go. 3,300 ohms will give me a temperature reading of 12 degrees, which then that comes in line with the ambient air temperature. So let's see if it'll start. What I also want you to look at is the fuel pressure here to see if that's rising. When I crank it, that should rise to somewhere in the region of 30,000 kPa, and also as well we should see glow plug control. So we'll leave the fuel pressure at the top of the screen. We should see glow plug control starting to come in as well. As you can see, still doesn't start with the intake air temperature sensor bypassed to give a true value of the temperature within this workshop now. The fuel pressure, I think you would have seen rising to above 30,000 kPa as well, so we're happy that we've got sufficient fuel pressure to allow this engine to start. Now what we could do now is we could go around individually and test the fuel pressure. Has it got enough fuel pressure? Are the glow plugs, even though they're being commanded on, are they coming on? Blah, 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 blah. Is the timing correlation correct on the engine? But there's one simple way to do all these tests in one hit, and it's using an oscilloscope. So what I've got is I've got 3 channels hooked up at the minute. I've got a low amps clamp on an injector. I'm back probed into a glow plug to see if the glow plugs are being commanded on. And I've got a high amps clamp on the negative cable of the battery as well. Now, when I crank this engine, what I'm going to see is I'm going to get a relative compression test of the engine from the low amps clamp. I'm going to see on the yellow channel if the glow plugs are being commanded, and then also I'm going to see if the injectors have been switched on. Now, if the injectors have been switched on, that tells me a lot. It tells me I've got sufficient engine speed. The engine speed must be above 250 RPM. I've got camshaft and crankshaft sensor in correlation, so the relationship between the two sensors, the engine ECU, is seen as good. I've got sufficient fuel pressure in the fuel rail, so basically above usually about 20,000 kPa, 200 bar. As long as it sees all of those inputs and it likes those inputs, it will then switch on the injectors. So in one test here, I'm going to do a relative compression test. I'm going to see if my glow plugs have been switched on, and I'm also going to see if the injector has been switched on, telling me I've got fuel pressure, I've got cam crank correlation, I've got sufficient engine speed. So basically I have a start permission signal. But also as well, the data that I capture from this as well, I'll be able to then get a good view of the condition of this engine via compression. And I'll also be able to tie it in with an injector, so I can then actually see if there is a low compression issue on one cylinder, etc. I can then tie it in to see which cylinder has got the compression issue. I'm now going to put the camera onto the oscilloscope screen, and I'm going to crank the engine and let you see the data that's been recorded. I want you to ignore the blue channel because that's not being used at the minute. The gold yellow channel, channel D, is the glow plug command. The red channel is the injector, and the green channel is the starter motor amperage. So what we should see is on the green channel we should see a sawtooth. On the red channel we should see the injector switching on, and on the gold channel, the yellow channel, we should see the glow plugs being switched on. So I'm going to go and crank the engine and see what we get. Cranked it there just until it tried to start. So what we'll do is we'll stop the scope and we'll go back. So straight away I can see in the red channel injectors are being switched on. So after one revolution of the engine, because there's 1, 2, 3, 4 compression events, the injectors are starting to be switched on. On the gold channel I'm seeing there's activity on these glow plugs, so I'm going to zoom in a bit further just so we get a better look at one complete revolution of the crankshaft. So we have the injector being switched on here and the injector being switched on here. So 1, 2, 3, 4 compression events, and then we're back to the first one. And as you can see, the glow plugs are being switched on because we see the switch on the glow plug circuit. So that tells us that the engine ECU on the diagnostic tool is telling me that the glow plugs are being switched on, and that proves to me that there's actually power getting to those glow plugs. So I'm happy that the glow plugs are being switched on. So if we look at the compression, so relative compression, what I'm going to do is I'm just going to tidy that up a bit. The dropouts and what have you see in this, if you look, are in line with the glow plugs. It's basically the glow plug current interfering with the starter current. And as you can see, the compressions, that one's a tad lower. Them three are about the same, and again that's a tad lower. So let's go along and see if the next lot of events are the same. So that's the next full rotation of the engine. It's there or thereabouts. So we've got a cranking amperage of 187 amps. Now, as a rule of thumb, I like to see a cranking amperage of about 3 times the battery's amp hour rating. So I'm going to check what the battery amp hour rating is. It's a 75 amp hour battery, so 3 times that, that's 150, 225. It's a little bit low, so has this engine got a compression issue? Possibility. The injector we're tied into is the injector which is the second injector away from the transmission, which I believe on this engine will be injector number 2. So if that's cylinder 2, so that's firing order is 1342, so that's going to be 1, 3, 4, and then we're on to number 2 again. So if there is a compression issue, as a cylinder with slightly lower compression, it's going to be that cylinder there. So maybe that's something we can put in the database, put in the memory bank for as the diagnosis progresses. But at the minute, I'm seeing glow plugs switched on, I'm seeing injectors switched on. So there's heat in the cylinder from the glow plug, injectors are switching on, so it means I've got sufficient fuel pressure, I've got sufficient engine speed, I've got a cam-crank correlation, then bingo, start permission signal. Engine ECU will switch on injectors. I've got 4 compression events which are there or thereabouts. One is slightly lower than the rest, but if it was a problem just on one cylinder, I would expect the van to start and maybe run a bit rough. And the rough running would be a slight misfire because of a lack of combustion in that cylinder, which has got the slightly lower compression. And as the temperature rises in the cylinder, it would normally even out, and also as well we'd get a bit of smoke at the tailpipe as well. Next test, the engine ECU is seeing fuel pressure. Does the fuel pressure actually exist? And also as well, it's switching the injectors on. Is the fuel actually getting through the injectors and into the cylinder? How do we test that? We could take an injector pipe off and put a gauge between the fuel rail and the injector and measure the pressure there. That's one way. To actually find out if the injectors are delivering fuel, we would have to remove an injector and have it bench tested. All intrusive tests. There's an easier way to do this. What I'm going to do is I'm going to point the camera at the tailpipe of the van, and I'm sure what you're going to see when I'm cranking this engine is grey smoke at the tailpipe. The only way grey smoke can exist at the tailpipe is if fuel has been injected into the cylinders. Next test, let's check the tailpipe. So I've got the camera pointed at the rear bumper of the van now. Tailpipe's on the passenger side. I'm now going to crank the engine and see if we can see any smoke at the tailpipe. And yes, there was smoke at the tailpipe. So again, conclusively, I'm getting fuel injected into those cylinders. We're going to have to go a bit deeper now to try and work out why this engine is struggling to start. I think at this point in the diagnosis, the time has come to sort of step back, have a look at the data that we have captured so far, have a cup of tea, and have a think about it. What does this engine need to start? It needs sufficient compression to generate enough heat within the cylinder so that when the fuel is injected, it turns from atomized fuel to vaporized fuel and then ignites. It also needs sufficient air coming into the engine to be able to achieve that compression as well. So we know straight away, we know that we've got fuel getting injected into the cylinders. At this point we could say we've got bad injectors. Now this is where the last garage, this is the route they went. They had the injectors taken out of the engine, they sent them to a fuel shop and they had them tested. And what the fuel shop came back with was that the injectors were actually under fueling. So that's what prompted that garage to replace the 4 injectors. Now I've checked and they have been replaced with brand new units and not reconditioned units. So we can guarantee that the injectors are going to be atomizing. They've also replaced the high pressure fuel pump. What the reason for that was, I don't know, but again, we can see that the engine is capable of producing fuel pressure, or the fuel pump is capable of producing sufficient fuel pressure to start. We saw the smoke at the tailpipe, so we know that the fuel is being injected. The fact that we see the grey smoke at the fuel pipe is the fuel has been injected, but it's not been ignited, but it is turned into a vapour, which is probably due to the heater plugs. The heater plugs are coming on, they are upping the temperature in the cylinder sufficiently to turn the fuel to vapour, but there's still not enough temperature in the cylinder to actually ignite that fuel. So this is the route I'm going down. I'm looking at what can be the cause of a lack of temperature in the cylinder, and it's got to be compression or something going on within the cylinder. Now before I go any further, I want to prove to you that this van does actually start. So I'm going to crank it and crank it and crank it. I've got it on battery support and it will eventually start. And the reason I wanted to get it running is because when I do the next test, I want you to see that the engine is actually capable of running. So there we go, it's running. I don't know if you can hear it so well, but it's running quite well. It's not misfiring. But what I do notice is, when it is running, to me, it sounds like the engine tone is a bit muted. Now, the best way I can explain this is, if we go back a couple of generations of diesel engines when we had either rotary or inline pumps with separate fuel pipes for each injector coming directly from the pump, if we retarded the fuel timing the engine noise would sound muted. If we advanced the fuel timing, the engine noise would sound a bit harsher. It sounds like a retarded diesel engine. I might be overthinking this, but it's just what it sounds like to me. I've been told that once it runs, it actually drives fine. The guy who owns the van has never complained of any lack of power. What you can, I don't know if you can see, there's a bit of diesel smoke in the air, I can smell it. So whether that's a result of me just cranking it and there's lots of unburned fuel up the exhaust, or is it just a bit smoky when it's running. Next test, what I'm going to do is I'm going to take a glow plug out and I'm going to go in cylinder and see if I can get any more evidence from the in-cylinder waveform. Now, to get that in-cylinder waveform, I need to remove a glow plug. So that's going to be the next thing. The glow plugs are stuck down the back of the engine, just next to the injectors. So I'm just going to remove one of the glow plugs. They're a bit of a, there's an art to getting these out. Got my socket on it now. There we go, one glow plug removed. And I'm going to replace the glow plug with this adapter, which is out of a compression test kit. If I could find the hole, make your own jokes up about that one. We'll then attach this pipe to it, which is an AST to WPS adapter pipe. I've got my WPS pressure sensor, which I'm then going to attach to the end of that pipe. But first, before I do anything, I'm going to unplug all of the injectors, because what I don't want is this engine to start while I've got my WPS plumbed into it, because it will blow it to bits. So the injector's plugged, and we'll now connect that up to the oscilloscope, and we'll give it a crank, and we'll see a pressure waveform on the screen. So with only channel A displaying on the scope, because that's where I've got the WPS pressure transducer connected to, I'm going to switch the transducer on, and you should see it go through its zeroing sequence on the screen. There we go. So that's basically zeroed it to zero. So I'm now going to crank this engine, and we should start seeing a waveform appear. There we go. We'll dissect this a bit. So first of all, I'm going to measure the compression. 18 bar. Not great for a diesel engine. I would expect to see in excess of 20 bar of pressure. So that's the first thing we see. I'm going to zoom in on an event which is midway through the cranking sequence. So I'm going to zoom into there, and now what I'm going to do is I'm going to chop this into 4, which is going to show me the 4 strokes of the engine within that cylinder. There we go. So just to explain, if anybody doesn't know what we're looking at here, these are the compression towers. So between here and here, we have 720 degrees of crank rotation. So that's 2 rotations of the crankshaft, 1 rotation of the camshaft, so 1 full cycle of the engine within that cylinder. So the compression is rising here, so the piston is on its way up. It gets to peak compression. the piston changes direction, and this would normally be the power stroke, but as the engine hasn't started, we're going to call this the expansion stroke. The piston is coming down the cylinder, and then we're now at 180 degrees. 180 degrees is bottom dead center. So bottom dead center, and then we're going to start going back up again on an exhaust stroke, and then again back down again on an intake stroke, and then again back up again on a compression stroke. Now, as you can see, there's a bit of a dip there. What that is, that's what's called expansion. So if we put another line in and we put that to 0, which is in all intents and purposes atmospheric pressure, you can see that line is in line all the way along there because we've got an open intake. The exhaust system is at atmospheric pressure. The intake manifold is at atmospheric pressure. This dip here is where the piston is coming down and there's still no valves open on that cylinder. So what it starts to do, it starts to create negative pressure within the cylinder, or starts to create a vacuum. And we can measure the level of negative pressure by bringing that down there. And we've got minus 477 millibar of negative pressure within the cylinder. Now also what we can do as well, if we zoom in on there, like so, we can actually look where the pressure starts to change. We can see at that point there, the exhaust valve has opened. So if we set that about there, I'd say, and go back, our exhaust valve is opened at 152.4 degrees, which is 38 degrees before bottom dead center. Is that right? Is that wrong? I don't know. I don't know what the timing of this engine is. I don't know what the timing of the camshaft is. Now, what we can't see on this capture is the inlet valve opening. The reason being is it's a diesel engine, so the inlet is always running at atmospheric pressure or above because it's turbocharged. It will very rarely drop below. The only time it will drop below is when the throttle body closes, when the EGR is active. And the exhaust is at atmospheric pressure as well because that's vented to the atmosphere. So what we're not seeing is any pressure changes around the point where the exhaust valve would close and the inlet valve would open. So it becomes difficult to diagnose what's going on around about bottom dead center under these conditions. But there's a way that we can do this, and I'll show you how. Now we've got that waveform on the screen. What I now want to do is, to get a bit more definition on that waveform, I'm going to actually block off the air intake so that I can create negative pressure in the inlet manifold, which will give better definition so I can actually see the valve events occurring. So first of all, I'll take off the intake pipe on the throttle body, and I'm going to block it with this adapter here from my smoke tester, which I've got blocked off. And I'm going to put that onto the throttle body so that then closes the inlet manifold, stops it drawing any air in from the throttle body, so a vacuum will start to occur within intake manifold. So there we are, zoomed in. I've dragged the rules in. As you can see, where the pressure drops here is where the inlet valve opens, where the pressure rises here is where the exhaust valve opens. So exhaust valve, similar sort of degrees, 150 degrees, 152 degrees. The inlet valve is opening at 371 degrees. So basically 11 degrees after top dead center. Is that good? Is that bad? I don't know. I would be very surprised if I can get this data off the Ford technical site, because I honestly think in the dealerships they're probably not going to go this far in depth. So I don't know if this information is going to be available. Easiest way to compare it would be to find another vehicle with this engine and capture an in-cylinder waveform from that other vehicle. And then we can compare what we know is good from a vehicle that starts fine, doesn't have any running issues, with what we've just captured here. Now, what I've also done is I've took in-cylinder waveforms from cylinders 2 and 3 as well, which I have stored on file on this computer, and I'm going to show you those as well. I haven't done cylinder 4, the reason being is to get the glow plug out of cylinder 4 would mean quite a bit more dismantling because there's an aluminium casting in the way of that glow plug, and I don't really want to start dismantling components off the engine that I don't need to. What I'm going to do now is I'm going to bring up cylinder 2, which is that one there. And again, same waveform or similar. Our exhaust valve is opening around about 159 degrees before bottom dead center, and our inlet valve is opening 378 degrees, which is 18 degrees after top dead center. And then if I show you cylinder 3, exhaust valve opens at 155. Inlet valve opens at 373, so that's 13 degrees after top dead center on the exhaust stroke. So there's a variation there, they're not identical, which that in itself basically rings alarm bells. So like I said before, I needed something to compare this with. One of my neighbours here, 2 doors down, has a Connect van. It's slightly newer, but what I did was I ran the VIN number for this van and the VIN number for his van through Parts 24, and I looked up the part numbers for the camshafts, and the 2 vans have identical camshafts, have the same part number. So I borrowed his van and I took a capture from his van, which is this one here, Connect Known Good, and straight away hopefully you'll see the difference. His exhaust valve is opening, I took a capture off one cylinder, is opening at 149 degrees, and his inlet valve is opening at 365 degrees. So his inlet valve is opening at 5 degrees after top dead center, and his exhaust valve is closing, what's that, 30 degrees, 31 degrees before bottom dead center. So there's a difference there. Could this be the problem with this van? Is it the fact that the inlet valves are opening late so that it's not getting enough air charge into the cylinder, so when the piston comes up it's not creating enough compression? So there we have it. Still up in the air with this one. I've reported my findings back to the garage that sent the vehicle to me. Going back over what we've already tested, we know we've got a start permission signal from the engine ECU because we have injectors switching on. We know that we have fuel being injected because we've seen the smoke at the tailpipe when it's not starting. We've done a relative compression test and the cranking amperage was a bit lower than what we expected to see. We've done an in-cylinder compression test using the WPS with an open air intake, and we've measured the compression on that cylinder, 18.5 bar, which I believe is low. I would expect to see in excess of 20 bar. So based on that, it looks like we have a compression issue with this engine, that's what would give us elongated cranking, bad starts. We've also looked at the valve timing events. Now, the valve timing events differ on this engine to the known good engine, and also they differ cylinder to cylinder. Now, not one cylinder that I tested came anywhere close to the, 5 degrees after top dead center of the known good engine for the inlet valve opening. The best was 11 degrees, I think, and the worst was 19 degrees after top dead center. So what could be causing that? It's an 8 valve engine. It has one camshaft. The exhaust valves and the inlet valves are both controlled with that single camshaft. If you look at the exhaust valve timing, there was a variation there as well. The exhaust valve opened earlier on the good engine than it does on our engine. The inlet valve opened earlier on the good engine than it does on our engine. That could point towards the camshaft being slightly out of time. But the variation across the 3 cylinders that were tested, there was a variation. That could point towards a problem with hydraulic lifters in the engine. The way this engine's set up, it's cam over rocker. It's got roller rockers. At one end of the rocker, there's a hydraulic lifter, and at the other end of the rocker is the valve. If those hydraulic lifters aren't holding oil pressure, it's the same as having a slack tappet on an old adjustable tappet engine. What will happen is the valves will open late and close early, because as the camshaft acts on them, the first thing to give is the lifter, and the next thing to give is the valve, where the first thing to give should always be the valve. The lifter is only there to take up the slack between the roller rocker and the back side of the camshaft. So I think there's enough evidence here on this vehicle to start going a bit more intrusive. Like I said, I've rang the garage that sent the vehicle to me. I've explained my findings to him. He's going to then speak to the owner of the vehicle, and they're going to decide between them whether I'm going to start dismantling this engine and looking a bit further. The first thing I would do is I would be removing the timing belt, and I'll be taking the sprockets off the crankshaft and the camshaft to look to see if there's any wear in the keyways. Bearing in mind this van has only done 39,000 miles. I'm not expecting to see that. I would hope not to see that. Because the way the cam and crank sensor pick up the signal, they're both picked up off the sprockets and not off the shaft. The crankshaft sensor looks at a reluctor ring, which is on the front of the camshaft sprocket that the timing belt runs on, and there's a keyway on that sprocket to locate that reluctor ring. So if that sprocket is worn or out of position on the crankshaft, that could cause the problem. The camshaft sensor, it looks at the back of the cam sprocket. So again, if the dowel or the keyway that locates that sprocket onto the camshaft has moved, worn, broken, and the cam sprocket has moved, again, this could cause this problem. The engine will still get its start permission signal because the relationship between cam and crank sensors is good as far as it's concerned, but the shafts themselves could be out of time. So, as I say, the first thing I'll be doing is taking the belt off, taking the sprockets off, and inspecting those keyways. If those keyways are okay, the next thing I'll be doing is taking the camshaft out of the engine and checking the hydraulic lifters. If this job goes any further, I'll do another video on it. But in the meantime, thanks for tuning in, thanks for watching. I hope you enjoyed this video. Like I said, we had the big guns on this one. We've used amp clamps, we've used pressure transducers, we've used decade boxes, just to try and get to the bottom of a bad starting issue. This is the level of diagnosis that I go to. I'm not saying that every garage goes to this. This is the level I go to. This is why people send vehicles 100 miles to this garage to try and find out what's wrong with them. I hope you appreciate the investment I'm making. in equipment, knowledge, training. That investment has to be paid for, and that is paid for via the price I charge to my customers. I always said I'm not the cheapest garage in the world, but I do offer good value for money. As yet, I have not fitted a part to this engine. The garage that sent it has fitted 4 injectors. Yes, they were tested and they were found to be faulty. They fitted a high pressure fuel pump. They fitted glow plugs. They fitted a mass airflow sensor. They fitted fuel pipes. They fitted a fuel filter housing and a fuel filter to this engine. If this vehicle had come to me in the first place, I wouldn't have done that. I would have gone down exactly the same route as I've gone today. I may have had the injectors taken out and tested. That's the only thing, that's the only caveat I would say. If I found the injectors were faulty, I would probably have changed those injectors. But anyway, thanks for watching. If you like what you see, subscribe to the channel. And if you want to see more videos like this, hit the bell for notifications. Also, get across to Facebook. I've also got a Facebook page, which is Intelligent Auto Ltd. Go over there, give us a like, give us a follow, have a look through some of the posts that we've put up. I do try and post regularly on Facebook, whether it just be pictorial stories rather than videos. But get over there, give us a like, give us a follow, and thanks for watching.